Okay, so we're going to look at the June 2010 ISA paper. This is Q, and we're going to look at the section B, which you can do without having done the practical. So the practical before this paper used an LDR as a way of measuring light intensity, and you were measuring it through tracing paper and seeing how it was affected by the distance from the tracing paper. But anyway, all of that's irrelevant because we're not using it. So the experiment we're going to think about now is similar, but with a gamma source. And we're measuring the distance from the gamma source, and we're going to measure the count rate at different distances. And the values in the table we're going to see in a second are called corrected repeat readings of the count rate. So explain why a correction has been made to the count rate values. Well, if we're measuring radiation, we're going to be using a Geiger counter, and we're also going to be measuring background radiation. So to correct it, we would have had to measure what the background count rate was and subtracted it. So we've only got the count rate from the source. So this is the data that's been collected. So we've got different distances and different count rates. And each count rate's been repeated twice to give us an average count rate. And then we've calculated 1 over count rate, the square root of count rate, which we'll look at later on. So first question, why would you take repeat readings at each distance? Well, there are two good reasons to do repeat readings. To check your results are reliable, so seeing you're getting consistent values each time. And also by calculating an average of repeat readings, it helps you reduce the impact of any random error on your measurement. So 2 part C, we want to estimate the uncertainty in C for D equals 14 centimeters. So if you look back at the table, and I've put a link to the actual paper in the description if you want to get this paper. So from the table, we can go to D equals 14. We've got 3 repeat readings. So we're going to do the range of the repeat readings divided by 2. That gives us 6 minutes to the minus 1. So theory predicts that C is inversely proportional to D squared, and the uncertainty in all the measurements of D shown in the table is 2 millimeters plus or minus. Estimate the percentage uncertainty in the value of 1 over D squared when D equals 2 centimeters. So first, let's get the percentage uncertainty in D. So we're going to take the uncertainty divided by the value. So they're both now in millimeters, and times by 100 gives us a 10% percentage uncertainty in D, which means the percentage uncertainty in D squared is going to be double that, squared 20%. The integer 1 doesn't add to our percentage uncertainty, so the percentage uncertainty in 1 over D squared would also be 20%. So looking at 2e, we're going to use the table and fill in the blanks. So here is our table. So the first thing we're going to do is get the average readings, and I'm going to give it to the nearest count, because that's what we can see all the way down the column. And on the next one, I'm going to give them all to 3 significant figures, because again, that's what you can see all the way down the column. So I'm just obeying the rules that have been followed in the column so far, 3SF. Okay, so those are our points. And as usual with these questions, what's coming next is plotting a graph, measuring the gradient, and then getting some value from it. So let's do that. So here's our graph. Here are the 2 values that we've just filled in the table, and you'd need to plot these to within a millimeter of the correct location. Here's the best fit line. So looking at it, we need to get roughly equal points above and below. So I can see 4 above, 3 below, so that's all good. And we want to get the gradient. So we want to do that over as much of the graph as possible. So that's what you can see. And then we want the change in y over change in x, and the gradient would give us 0.00785. So that's the gradient of this graph. Okay, so the last part, we want to find the value of k and state its unit. So if we look at the equation, on the y-axis we had 1 over root c, and on the x-axis we had d, which means k is the gradient. So that would be 0.00785. And the gradient will be the unit of y divided by the unit of x. So the unit of y is meters to the minus 0.5, or meters to the minus half, and then divided by centimeters, or centimeters to the minus 1. Okay, so the constant E in the equation is non-zero because all the measurements of D were consistently too small or too large. What kind of error is this? If it's consistent, that's going to be a systematic type error. So were the measurements of D too small or too large? Explain your answer. Well, according to the graph, D is negative when 1 over root C is 0. But we know D must have actually been 0 at that point. So what that tells us is D must have always been too big when in the measurement. So use your graph to determine a value for E. So the y-intercept is equal to k times E once you multiply out the brackets. Therefore, E is the y-intercept divided by k, and that's going to come out as 1.4. Okay, so the equation 1 over root C equals k times D plus E assumes gamma radiation spreads out equally in all directions from the source. Discuss whether or not the graph supports this assumption. So essentially the way I thought about it is if it spreads out equally in all directions, intensity should be inversely proportional to D. That's what we get with any kind of scenario when we have things spreading out from a point. So with radiation, as long as our detector area remains fixed, the count rate is going to be directly proportional to the intensity. So if you double the intensity, you should get double the count rate. So the graph shows that C is inversely proportional to D squared. And so therefore it does support that assumption. So describe how you'd use the apparatus you used in practical task stage 1. So that was using the LDR, if you remember from right at the start of this video, to find out if the light from a lamp also spreads out equally in all directions. So an LDR, you can measure light intensity by, or what's happening to light intensity by measuring resistance. So an LDR's resistance is inversely proportional to the light intensity. So we're going to have an ohm meter connected to our LDR. And if we want to check that it spreads out equally in all directions, we need to measure the LDR resistance at different points that are equidistant from the source. So we can essentially go round in a circle from the source. But we need to make sure that the area of the LDR pointing at the source is constant, because area can affect intensity as well. So we need to make sure the same area is pointing at it. And if the resistance readings are the same at the same distance, that would mean the light intensity spreads out equally in all directions. And that completes this paper for the ISA.